For this video, I'm going to take you through some specific examples of matrix multiplication in 3D, and the purpose of that is to show you how matrix multiplication works in 3D. Now, I could just go through the rules by themselves, but I feel like this is a better approach because you can actually see those rules in action. And if you do want a better overview or you're fairly new to the concept, then I'd recommend checking out my video on matrix multiplication in 2 dimensions and 1 dimension. Which is on my channel. You can search it up. So this is going to be looking at matrix multiplication for Numpy in 3 dimensions. Now, the rule still holds, and it might look a little bit confusing because now there's 3 dimensions to go off. So truly we have another variable here representing the 3rd dimension. But you'll see what I mean when I say that this rule still works. So just to remind you, if you have an n by k array and you have a k by m array or a matrix, then as long as k is equal to k, then it will work, then the matrix multiplication will work and it will result in an n by m matrix. So let's look at this first example here. So we have a 3-dimensional array here and we have a 1-dimensional array here. Let's look at the shapes. Let's just print the shapes here. Oh, we need to import Numpy first. Okay, so we have a 3 by 2 by 4 array and we have a 4 comma nothing array. If you remember from my last video, which was on matrix multiplication in 2D and 1D, I was saying how Numpy has a rule where if you have a 4 comma or you have a 1-dimensional array that's going in, it actually converts it to a matrix beforehand using this rule here. So I'll just show you to remind you. If the first argument is 1D, it is promoted to a matrix by prepending a 1. And if the second argument is 1D, it is promoted to a matrix by appending a 1 to its dimensions. And then after matrix multiplication, the prepended and appended 1 is removed. Okay, so what this will do, because we're going to compute the matrix multiplication of array 1, comma array 2. So array 2, which is 1-dimensional, is in the second argument. So therefore, it's going to append a 1, and the shape is going to look like this. 3, 2, 4, and 4, 1. So how are we going to use this rule here to see if matrix multiplication will work? And by extension, what is going to be the result? Because here we have 3 variables here in this array 1, and here we only have here we have 2 variables, so that's fine. But if we look at Numpy's documentation a little bit further, we can see that here, if either argument is nd, n greater than 2, it is treated as a stack of matrices residing in the last 2 indexes and broadcast accordingly. Just think about that for a second. And I'm going to show you what that means, and then we're going to return back to this definition so that you can solidify that. In the last 2 indices, this is the last 2 indices. Because this is a 3-dimensional array, n is greater than 2, so that rule applies. So in the last 2 indices, that's where matrix multiplication is relevant. This has 2 indices. So what we do is we just take these indices here and we use this rule. 4 is equal to 4, so this will work. It will create a 2 by 1 matrix at first, but then it will actually multiply that by 3. So the matrix that it will result is 3 by 2 by 1. Let's print out the result here. Well, actually, hang on. What it spits out at first, what it results in at first, is a 3 by 2 by 1 matrix. Because it is a 1-dimensional array here, it had to append a 1, so it had to add a 1 in the second dimension. So I'll just show you this again. So it started with a 4 comma, it converted to 4 1, and if this doesn't really make much sense to you, then I'd recommend watching the other video on matrix multiplication that I made first, or just looking through this documentation briefly by yourself to understand these 2 rules. But I go into these in detail in the other video, so it's up to you how you want to look into it. But anyways, first it does this, and then after it performs matrix multiplication, it results in a 3 by 2 by 1 matrix. But then, after the matrix multiplication is performed, this has to, the 1 has to be removed because it added a dimension, and now it has to remove that dimension that it added. And that's why it removes this 1 dimension, it squeezes it, and we're left with a 3 by 2 matrix, which is this one, 3, 2. Now I'm just going to see if I have, no, I don't have that example there. But for example, if I did, what is this, 4, 1, so if I converted this to a 4, 1 matrix, which looks like this, 4, 1 like that. Now, array 2 and array 1's shape. So this array 2 is completely equivalent to the previous one in terms of its values, but now it's just a different form. Now it's in a different shape. So now we have a 4, 1 matrix. Now if we perform a matrix multiplication, it's going to result in a 2 by 1 matrix extended over three elements. So now it is going to result in a 3 by 2 by 1 matrix. If we print it out, we get 3 by 2 by 1. So it's 3 by 2 by 1. If we print the shape, there you go, 3 by 2 by 1. But because array 2 was originally just like this, it actually squeezed it. Hang on, like this, there we go. It squeezed it, and then it's 3, 2 shape. So that's the way it works. Firstly, it performs the matrix multiplication it needs, and then it removes the dimensions if it requires that, if it actually extended the dimensions in some place. Okay, so that's what it means by it's treating, if we look back to here, stacks of matrices are broadcast together. Oh, hang on, no, we were looking over here. It is treated as a stack of matrices residing in the last 2 indexes and broadcast accordingly. So that's if either our argument is at least 3-dimensional, which in our case it was. Now let's look at actually what goes into it. So we figured out the shape and why the shape looks like that. But now let's look at the values. How is it actually being matrix multiplied? What we'll do is, so we're matrix multiplying this one by this one. Okay, so firstly it converts it to a 4, 1 matrix. So that looks like this. That's what it does. And then it performs the matrix multiplication. Okay, so how does it do that? So it looks like it performs a matrix multiplication with each of the elements through the 0th dimension. And in the 0th dimension is this outer one here. That is each of these blocks here. So this is the 0th element in the 0th dimension. This is the first element in the 0th dimension, and this is the second element in the 0th dimension. So it treats each of these elements through the 0th dimension as its own matrix. And then it performs matrix multiplication, which is taking the dot product of this row with this column, that'll be 30. And then taking the product of this one with this one, that'll be 70. And now originally, let's just actually get, just so it's not so confusing. I started, looks like I started with a complicated example, but that's actually fine because that means that the rest of the examples are going to be easier. So now if we perform, there we go. So this is the result that comes out when we perform this matrix multiplication over here. So there's going to be a dot product between this row and this column, and that's going to be this value here. Then there's going to be a dot product between this row and this column, which is this value here. And the reason it's downwards is because we're moving down the row here. So it is going to be down. For example, if we had more columns in this matrix and we had to move to the right, like let's say we were taking the dot product of this one, of this row, and then a column over here, then we would move to the right of this resultant matrix. Okay, so that's this first section here. And then we need to move down to this second element through the 0th axis, which is this one here. So we do the same multiplication. We take the dot product with this row and this column, then this row and this column, and that's going to be these values here. And notice how they're in the same index in the 0th dimension. So this is index 0 of the 0th dimension. This is also index 0 of the 0th dimension. This is index 1 of the 0th dimension. This is also index 1 of the 0th dimension. So note that every element in the 0th dimension is taken as its own matrix. And it does the same with this last element here. This row is taken with this column, and this row is taken with this column. And just to show you that I'm not lying here, if we perform matrix multiplication with, I don't know, this row and this column, for example, just making sure that I wrote that right. Yeah, that is right. We get 150, and that corresponds to this value here. So there you go, that is the first example there. Let's take a look at the next example, and it should be a lot easier now because, well, we picked quite a challenging one. All right, so let's take this downwards a little bit. What do you think the shape is going to be for these two arrays? Well, this is the 0th element in the 0th dimension. This is the first element in the 0th dimension, second element, third element. So that's going to be 4, because there's 4 elements there. 4 by, then we have 2 elements through the first dimension, so 4 by 2, and then we have 4 elements through the second dimension. So that's 4 by 2 by 4. So if we print out the shape of, well, that's arrays 2 shape. Oh, that's arrays 1 shape. So I've actually swapped this around. So this is going to be performing matrix multiplication with array 2 and then array 1. But let's look at the shapes. So we have 4 by 2 by 4 for this array here. And then array 2 shape is 1, 2. Now the reason I've written it like this is because we're performing matrix multiplication with array 2 in the first argument and array 1 in the second argument. So I've written it with array 2 first and then array 1 second. Okay, is this going to work? Let's test it out. Does work. Okay, let's look at the shape just over there. Now, why does it work? It's not matrix it's not treating these two or these 4 elements as the rule. It's not treating this as the matrix and then this as the matrix. Because array 1 is a 3-dimensional matrix, then it is treated as a stack of matrices residing in the last 2 indexes and broadcast accordingly. So the last 2 indexes of array 1 are these ones. So essentially it's treating 1, 2 and 2, 4 as the matrices. 2 is equal to 2, so it's going to create a 1, 4 matrix. And then that's this one here, that's just one of these, but then it's broadcast. So it's treated as a stack of matrices, and there's 4 stacks of matrices, so it's going to do that 4 times. And because Numpy has not had to use the rule, these 2 rules, has not had to use these 2 rules to extend the dimension in the in a 1-dimensional array, then it hasn't had to remove the dimension in the final array, so we're actually left with the full matrix here, or the full array in 3 dimensions. So that's why we get a 4 by 1 by 4 matrix. And if we look at the shape here, there's 4 by 1 by 4. Let's look at the elements. Where does it come from? Okay, so array 2 is first. So array 2 is over here. I probably will end up actually just writing it out like this. There we go. So array 2 is first. Now what happens? Array 2, because it's first, each row is taken. So this row is taken with this column here, 1, 5. Then 1, 2, this row, the same row, is being, the dot product is taken between 1, 2 and 2, 6, then 1, 2 and 3, 7, and 1, 2 and 4, 8. So for example, times 1 is 4, plus 2 times 8 is 16, so that should be 20, and we do get a 20 there. And now we're moving through each row in this array. This is array 1. So we're moving through each row in this matrix here. So we're going to move through each row in the resultant matrix. And that's why 1 times 1 plus 2 times 5 is here. And then 1 times 2 plus 2 times 6 is to the right, is 14. There we go, 14. Okay, so it performs that once. But now when we don't have this first argument here, that is not a three-dimensional array. This second argument is a three-dimensional array, so we're going to move through each element in the 0th dimension. So then 1, 2, this matrix here is going to be matrix multiplied by this matrix, and that results in this result here. And then we move down this element here to the second element in the 0th dimension, because we have 0, 1, 2. And then that's matrix multiplication between this and this, that results in this this result here, 59, 62, 65, 68. And the reason that these are the same is because these are the same. Okay, so that's how that works. Now let's look at the next example. And what have I done here? This, I believe, is just the same situation, except now array 2 is one-dimensional. And we're going to look at matrix multiplication between array 1 and array 2, and then array 2 and array 1. Okay. Let's print the shapes for array 1 and array 2. So we have 4, 2, 4, and then 2, Now array 2 is a one-dimensional array, so Numpy has to use one of these rules. And it is in the second argument, so it has to use this rule here. It is promoted to a matrix by appending a 1 to its dimensions. So we add a 1 to its dimensions, and we're left with 4, 2, 4, and then 2, 1. And then array 2 will look like, well, actually it won't look like that. It will look like this. I'm just going to write it out here so that we can keep the other one if we need it. 1, 2. That is 2, 1 in terms of the shape. So once the rule is applied, array 2 is going to look like this, and we're left with these shapes here. Is this going to work? Let's test it out. It does not work. Now why is that? The reason for this, if you look at these two shapes, now this is a three-dimensional array here. So we're using this rule. If either argument is n-dimensional, where n is greater than 2, it is treated as a stack of matrices residing in the last two indexes. These are the last two indexes, and then we have this matrix here. Do these indexes meet the rule from earlier? Meet this rule. Was it n, k, k, m. So k has to be equal to k. They do not, because 4 is not equal to 2, so this matrix multiplication will not work. So that's fine. It can't be performed. But now let's look at the next one, which is matrix multiplication with array 2 and then array 1. So we can get rid of this one because we're starting with this original A2. Let's print the shapes of now array 2 and array 1, because now it's reversed. So we have to print arrays 2 shape first, because now it's in the first argument, and then we print arrays 1 shape. Now arrays 2 shape, that's 2, and then we have 4, 2, 4 for array 1. Okay, so the first argument is now one-dimensional, so we have to promote it to a matrix by prepending a 1. And what array 2 looks like when you prepend a 1 is it looks like this. There's just another dimension being added over here. So now there's 2 brackets because we have, what is it? So now we have 1, 2, prepending a 1, yeah, 1, 2, and it's going to be 1, 2. So it's going to look like this, 1, 2, and then 4, 2, 4. because we're prepending a 1, which means adding it before. So the most outer dimension, because this is the most inner dimension and this is the most outer dimension. It's kind of reversed like that. Okay, so once Numpy applies the rule, then the array looks like this. And now it's going to do matrix multiplication. Now, will this work? Does this satisfy the rule? It does. And the reason for that is because 1, 2 is being compared against 2, 4, because these are the last two indexes of this array. So 2 is equal to 2. We're going to get a 1, 4 matrix. It's going to become a 4, 1, 4 matrix. But then the dimension is removed because this had to be converted, or wait, hang on. This had to be converted to this. So the dimension needed to be added. But then, as per Numpy's notes here, after matrix multiplication, the prepended 1 is removed. So let's say we start with this one. Let's say that Numpy has not actually had to add the dimension, and then we print the result. We get 4, 1, 4. That is the shape, and that is 4, 1, 4. Because we originally looked at the rule for these two. We have 1, 2 and 2, 4. 2 is equal to 2, so it works. It results in a 1 by 4 matrix, but then it's broadcast along each of these 4 elements. So you have a 4, 1, 4 matrix. And if we print the shape here, it's 4, 1, 4. But because we originally actually started with this array here, which is one dimensional, Numpy first converts it to this one, then it performs matrix multiplication, which results in this, but then it takes away the dimension. So now if we print it out, we get a 4, 4 matrix. So that is, just to reiterate, originally we get a 4, 1, 4 matrix, but we had to remove the dimension. So we're left with a 4, 4 matrix of the same values. All right, and the values here, it works the same way as it does in the previous elements. Like for example, array 2's first. So we have this multiplied by this, then 1, 2 multiplied by 2, 6, then 1, 2 multiplied by 3, 7, then 4, 8, and then we move down to this next element and we do the same process. And that's going to be then this row here. All right, now we're going to the next example. Okay, so now we're going to look at a 3D array with a 2D array. Let's see how this works. What are the shapes of each of these arrays? They are 4, because there's 4 elements here, comma 2, because there's 2 rows, there's 2 elements through the column, and then comma 4, because we have 4 elements through the row, and that's what we get for the array 1. And then array 2, we have 3, 4, so that's 3, 4 here. Will this work? All right, well, this is a 3-dimensional array. So we take the last 2 indexes and we compare it to this array here. Is 4 equal to 3? It's not. So I'm not going to pause long for that because it's not too crazy of a statement to say that 4 is not equal to 3. When we print it out, we get an error. And it shows, this result. K is not equal to K. 3 is different from 4. So this will not work. But what about this? So this is the same example in terms of the values, but first we're transposing array 2. And transposing means flipping the arrays, flipping the row and the columns around in terms of a 2-dimensional array anyways. So if we remove this dot t, this is the same example as the previous one, but we add the dot t. So now let's look at the shapes. 4, 2, 4, array 1 still has the same shape. And then the array 2's shape, now it's 4, 3 instead of 3, 4. If we print this out, instead of 3, 4, now it's 4, 3 because we flipped each of the rows and the columns around. So just to show you what that looks like, if we print array 2 from the first example, which is just this one here, 4, 5, 6, 7, 7, 8, 9, 10, 8, 9, 10, 11. and then we run this cell here, and we print array 2, now transposed, this is what it looks like. So 4, 5, 6, 7 is now the column, then 7, 8, 9, 10 is now this column, and 8, 9, 10, 11 is now this column. So it's just transposed it, and it's a simple operation there, but now we can see that 4 is equal to 4. So it's going to create a 2 by 3 matrix, and it's going to broadcast that 4 times. Here is another rule that Numpy's documentation has. Here you go. Stacks of matrices are broadcast together as if the matrices were elements, respecting the signature nk km is equal to, or results in n by m. So the matrices are elements. The matrices are elements. Each of these matrices are one element. That's what I was talking about before, where it takes each element of the 0th dimension and takes that as a matrix. So that's why you get 4 by 2 by 3. If we print the result, we get 4 by 2 by 3. And the shape, just to show that it's true, 4 by 2 by 3. Now, how does this work? Well, array 1 is first, and then array 2 is second. If we, how are we going to do this? If we print array 1 and then array 2 together like that, well, let's do it like this. Print array 1, print array 2. So array 1 is first because that's the first argument here. So the rows are going to be taken in array 1. So this row is going to be matrix, or is going to take the dot product with this column. Then this row is going to take the dot product with this column, then this column, and then it's going to move down, and it's going to take the dot product with this one, and this one. That is going to result in these values here. And then the same situation is going to happen with this element here, with this matrix, So this matrix is going to be matrix multiplied with this matrix, and that's going to result in this one. And it's going to move down because we're moving down here as well. That's why each of these are in the 0th dimension. So that's why each of these are in the 0th dimension as well. Okay, so that's that example. Now this one is a more complex example because we have a 3-dimensional array for both of these arguments. Let's confirm the shapes here. So we have 4 by 2 by 4, that's this one, and we also have a 4 by 2 by 4 matrix here. Is this going to work? It does not work. And we'll just print the shape again so you can see, or I can just print it down here. 2 by 4 compared to 2 by 4. 4 is not equal to 2, so it will not create a 2 by 4 matrix, and thus it doesn't matter about these values because this inherent quality doesn't match. So this will not run. Now what's the difference here? This is the same array as this one, as the previous example, but then the difference between this array and this one is we've switched some axes around. So let's take a look at, I'm going to run this previous example. I'm going to look at array 2. Is that the right one? Yeah, that is the right one. So that's array 2. And then once we actually swap the axes around, which is this example, I'm going to run this and then print out the result. So they're the same values. We have 1, 2, 3, 4, 5, 6, 7, 8, and that's just over here. And then 9, 10, 11, 12, 13, 14, 15, 16, that's just these values here. So the values are the same, but we've swapped the axes around. That's this one, np.swap axes, 1 with 2. So if we look at the shape, I'm going to have to run this cell again, and look at the shape of array 2 without swapping axes. And then we run this cell, and we look at the shape of array 2 after we've swapped axes. You can see that the dimensions are slightly different, or the shapes are slightly different. And that's because we've swapped axis 1 with axis 2, or dimension 1 with dimension 2. This is dimension 1, this is dimension 2. So before it was 2, 4, and now it's 4, 2. So we've just switched these around. So that switches the dimensions around, but the inherent values will stay the same. So that's why it just looks like a different shape to it. And the reason I've done this is because now if we print the shapes of these, array 1 is the same in this example, 4, 2, 4, but now array 2 is 4, 4, 2. Now, if we have this array and this array, 4 is equal to 4, so that works, and it will create a 2 by 2 array, and then that will be broadcasted 4 times. Let's print it out. That's the shape. So we have 2, 2, that comes from here and here, 2, 2, and that's broadcasted 4 times. 1, 2, 3, 4. So essentially I'll print out the arrays again just so you can see. This matrix here is now being matrix multiplied with this one. Then this matrix here is being matrix multiplied by this one. Then this one with this one. So when you have two 3-dimensional arrays, it actually moves down each element in both of the arrays. And that's these results here. So the first one here, array 1, being matrix multiplied with this first one here, that results in this here. And then as it moves down, it goes down here. That's that example. All right, here's the next example. And now what are the differences between these? Don't worry too much about the values here because I believe they're actually exactly or very similar to the previous values. Now the difference is the first array is still the same, 4 by 2 by 4, but now the second array is 4 by 4 by 3 instead of 4 by 4 by 2. The same concept holds. 4 is equal to 4. We get a 2, 3 matrix and it's broadcasted 4 times. So we get a 4, 2, 3 matrix. There you go, 4, 2, 3. And the same situation holds, like, so this is matrix multiplied with this, and then this is matrix multiplied with this, and that's each of these results. All right, another example. We look at the shapes of these. All right, so we have a 4, 2, 4 array, and this is being matrix multiplied by a 5, 4, 3 array. Okay, so both of these arrays here, they're both 3-dimensional, so we use this. It is treated as a stack of matrices recited in the last 2 indexes and broadcast accordingly. Okay, so the last 2 indexes, 2, 4 with 4, 3. 4 is equal to 4, and that'll create a 2, 3 matrix. Will this work? Let's try it out. What is this? So it doesn't work, no. And we actually get a new value error here. Operands could not be broadcast together with remapped shapes. Okay. So what does this mean? So this rule holds. 4 is equal to 4 and it results in a 2, 3 matrix. But then it's broadcasted, 4 or 5 times? Now there's different, now these are different values. So before these were the same values. Before we had 4 is equal to 4, but now we don't have that. Now we have 4 is not equal to 5. And that is enough to actually make it not work. With exception, there is an exception if one of these values is equal to 1, and I'll show you that in a second, but otherwise, if this value is not equal to this value, and one of them is not equal to 1, or 2 of them, then it won't work. Because, well, think about it. So we have this being matrix multiplied with this being matrix multiplied with this being matrix multiplied with this, and then this one with this, but then what? There's still another matrix over here, but there's no matrix over here to matrix multiply it by. So we can't actually, it doesn't make sense. That's the way that Numpy treats it. So if there's not a match in the elements through the 0th axis, which is each of these matrices here, for example, this one and this one, if there's not a match in the number of elements, then it won't be able to perform a matrix multiplication, because how would it do it? It wouldn't really make sense. That's why this example doesn't work. All right, let's look at the next example here. Okay, so this is a bit of a different example. We have a 4, 2, 4 array being matrix multiplied by 1, 4, 3. So we look at these indices here. 4 is equal to 4. So we get a 2, 3 matrix. Now in the previous example, this value was not equal to this value. And it is that case for this example as well. But when you have a one dimension here, then that's an exception. Because then it kind of makes sense when you do the matrix multiplication. This can be matrix multiplied with this. Then this can be matrix multiplied with this, with the same matrix here. Then this can be matrix multiplied with this. So it works the same, it works in this case. Like, it makes sense. You kind of have to think about if it makes sense. That's kind of like, that's why this example doesn't work, because there's 4 elements here and there's 5 elements here through dimension 0. So it doesn't make sense to matrix multiply them together. But this one, it does make sense. So it's okay that this value is not equal to this value, because this value is just 1. So it would still make sense. Each of these matrices here can be matrix multiplied with this same matrix in array 2. We print it out and we get a result, and the result is 4, 2, 3. And that's the result. All right, a couple more examples. Let's look at the shapes. So we have 4, 2, 4 being matrix multiplied by 2, 4, 3. Now the reason I gave this example is because you might think that, okay, so it has to make sense. So this could, by extension, make sense, because this matrix can be matrix multiplied with this one. Then this can also be matrix multiplied with this one. But then these two can each be matrix multiplied by this one. Or you can kind of divide each of these elements, each of these 4 elements, by 2, and then you could say half of them could go into this matrix, and then half of these, which is these 2 matrices, could go into this. But it turns out that it doesn't work that way. So either these 2 values need to be equal, or at least one of them needs to be a 1. If that didn't make sense to you when I was like explaining how half of these need to go into this, and then half of these need to go into this, don't worry about it. That's just something that someone could potentially argue if they were saying, okay, well, that makes sense. But essentially this won't work. So that's the point of this example. So 4 is equal to 4, but then 4 is not equal to 2, and none of these are 1. All right, let's take a look at the last example here. Okay, so I've just included this one because it's kind of interesting. Just have a look at it for a second, and then think about the shapes. Those are the shapes. And now, will this work? 1 is equal to 1. It will result in a 1, 2 matrix, and then it's going to be broadcasted only one time. So it's going to result in a 1, 1, 2 matrix. Let's print. It's 1, 1, 2. And now, what is it actually doing here? Array 1 is in the first argument, so we can write that there. And then array 2, this is the symbol for matrix multiplication, by the way, is in the second argument, so we can write it there. Now the first argument, the rows are taken, and we only have this one row, which is 3. And in array 2, the columns are taken, and we only have one element in each column, which is 2 and 4. So 3 is multiplied by 2, that gives 6. And then 3 is multiplied by 4, which gives 12. So this is just really like a fancy little example that highlights that sometimes it can work out even if it doesn't really look like it makes sense. But yeah, it still follows the inherent rules, like 1 is equal to 1, and then these two values are, well, at least one of them is 1, so that's fine. So it still follows the rules, but when you look at this, you might think that it doesn't really make sense to matrix multiply them together, and maybe it wouldn't, but it results in an answer and it doesn't give an error. Anyways, that is matrix multiplication in 3 dimensions. So you can see that it's a little bit more complicated than 2 dimensions and 1 dimensions, but it kind of works. It still follows the same inherent rules. They're just kind of extended in a way. But yeah, that was matrix multiplication in 3 dimensions, and I'll see you at the next video. Bye.